In the center of a galaxy called Holmberg 15A, roughly 700 million light-years from Earth, there exists an object so massive, so incomprehensibly large, that its event horizon could swallow our entire solar system and still have room for dozens more. This supermassive black hole weighs in at approximately 40 billion times the mass of our Sun. But that's not even close to the largest one we've discovered. That honor goes to an object known as TON 618, a black hole so massive that it tips the scales at 66 billion solar masses. Its event horizon, the point of no return beyond which not even light can escape, stretches across 300 astronomical units. To put that in perspective, the distance from the Sun to Neptune, the outermost planet in our solar system, is about 30 astronomical units. The event horizon of TON 618 is more than 40 times wider than our entire solar system. If you were traveling at the speed of light, it would take you nearly a week just to cross from one side of its event horizon to the other. A week at the speed of light. And we're just talking about the event horizon here, not the full extent of its gravitational influence, which reaches far, far beyond. These objects represent the most extreme environments in the known universe, places where our understanding of physics is pushed to its absolute limits and sometimes beyond. They are monsters in the truest sense of the word, cosmic predators that devour everything that comes too close, growing ever larger with each meal. And here's what should really keep you up at night. We're pretty sure there's one of these things sitting right at the center of our own galaxy. In fact, we're almost certain that nearly every large galaxy in the universe harbors a supermassive black hole at its core. They're not anomalies or rare cosmic accidents. They're everywhere. But for most of human history, we had absolutely no idea they existed. The story of how we discovered these cosmic monsters is almost as incredible as the objects themselves. Let's rewind to the early 20th century. In 1915, Albert Einstein published his general theory of relativity, fundamentally changing our understanding of gravity. Instead of being a mysterious force that pulls objects together, gravity was now understood as the curvature of spacetime itself. Massive objects like stars and planets create dips and curves in the fabric of space and time, and other objects moving through that curved space follow paths that we perceive as orbits. It was a revolutionary idea, and like most revolutionary ideas, it came with some strange predictions. Just a few months after Einstein published his theory, a German physicist named Karl Schwarzschild was serving on the Russian front during World War I when he solved Einstein's field equations for a very specific case. What would happen if you compressed all the mass of an object into an infinitely small point? The mathematics led to something bizarre. Schwarzschild discovered that if you compressed enough mass into a small enough space, you'd create a region of spacetime so severely warped that nothing, not even light, could escape from it. There would be a boundary, a point of no return, beyond which the escape velocity would exceed the speed of light. This boundary came to be known as the event horizon, and the mathematical radius at which it would form was named the Schwarzschild radius in his honor. At the time, this was viewed as little more than a mathematical curiosity, a weird quirk of Einstein's equations that probably didn't exist in the real universe. Even Einstein himself was skeptical that nature would allow such extreme objects to actually form. The term black hole wouldn't even be coined until 1967, when physicist John Wheeler used it during a lecture. But throughout the mid-20th century, astronomers kept discovering things that didn't quite make sense. In the 1930s, Theoretical work by Subramanian Chandrasekhar and others showed that there was a limit to how massive a white dwarf could be before gravity would overcome all the forces trying to hold it up. If a stellar remnant was too massive, it would collapse into something even denser, a neutron star. And if it was more massive still, nothing could stop the collapse. The object would shrink down past its Schwarzschild radius and become what we now call a black hole. By the 1960s and 70s, astronomers had begun to detect X-ray sources in the sky that behaved exactly like you'd expect a black hole to behave. These stellar mass black holes, formed from the collapse of massive stars, typically weighed between 5 and 100 times the mass of the Sun. They were the first black holes we confirmed to exist, and they were already pretty terrifying. But something strange was happening at the centers of galaxies. In the 1950s and 60s, astronomers discovered incredibly bright, point-like objects that seemed to be pumping out more energy than entire galaxies. Yet they were so compact that they varied in brightness over periods of just days or weeks. This meant they had to be relatively small, certainly much smaller than a galaxy. But how could something so small be so bright? These objects, dubbed quasars, remained mysterious for years. The explanation that eventually emerged was almost too wild to believe. Quasars were supermassive black holes, millions or even billions of times more massive than the Sun, actively feeding on surrounding matter. The material falling into these black holes would heat up to billions of degrees, emitting so much radiation that a single quasar could outshine every star in its host galaxy combined. But if these supermassive black holes were sitting at the centers of distant galaxies billions of light years away, was there one at the center of our own galaxy? This is where things get really interesting, because the story of how we confirmed the existence of Sagittarius A star, the supermassive black hole at the heart of the Milky Way, is one of the most impressive pieces of detective work in the history of astronomy. The center of our galaxy is located roughly 27,000 light-years away, in the direction of the constellation Sagittarius. There's just one problem. We can't see it. At least, not with visible light. There's so much dust and gas between us and the galactic center that trying to observe it with an optical telescope is like trying to see through a brick wall. But in the 1970s, astronomers discovered that the galactic center was emitting powerful radio waves. They found a particularly strong radio source right at what appeared to be the very center of the galaxy, and named it Sagittarius A star. Something was there. But what? The breakthrough came from decades of patient observation using infrared telescopes, which can peer through the dust that blocks visible light. In the 1990s, two teams of astronomers, one led by Andrea Ghez at UCLA and another led by Reinhard Genzel at the Max Planck Institute, began tracking individual stars orbiting near the galactic center. Using some of the most powerful telescopes on Earth, they watched these stars year after year, mapping out their orbits with incredible precision. What they found was remarkable. These stars were moving fast, really fast. One star in particular, designated S2, completes an orbit around Sagittarius A star every 16 years, and at its closest approach it's traveling at nearly 5,000 kilometers per second. That's almost 2% of the speed of light. For a star to be moving that fast, it had to be orbiting something incredibly massive. Using Kepler's laws of orbital motion, the same equations that describe how planets orbit the Sun, Ghez and Genzel calculated the mass of whatever S2 was orbiting. The answer? Approximately 4 million times the mass of the Sun. But here's the crucial part. Whatever this object was, it was completely dark. It wasn't emitting any light. It was invisible except for its gravitational influence on the surrounding stars. The only thing we know of that can pack that much mass into such a small, dark space is a black hole. In 2020, Andrea Ghez and Reinhard Genzel were awarded the Nobel Prize in Physics for this discovery, sharing the honor with Roger Penrose for his theoretical work on black holes. After decades of observations, we had definitive proof. There is a supermassive black hole at the center of our galaxy. But actually seeing a black hole, not just inferring its existence from the motion of nearby stars, remained elusive. Black holes are, by definition, black. They don't emit light. The event horizon itself is completely dark. However, the material falling into a black hole gets incredibly hot and does emit light, lots of it. If you could get a powerful enough telescope with high enough resolution, you might be able to see the glowing material swirling around a black hole and maybe even catch a glimpse of the shadow cast by the event horizon itself. There's just one problem. Black holes, even supermassive ones, appear incredibly small in the sky because they're so far away. Sagittarius A star, despite being 4 million times the mass of the Sun, would appear smaller in the sky than an orange on the surface of the Moon. No single telescope on Earth has the resolution to see something that small. So astronomers came up with an audacious plan. What if, instead of building one impossibly large telescope, they linked together multiple telescopes spread across the entire planet? Using a technique called very long baseline interferometry, they could effectively create a telescope the size of the Earth itself. This was the Event Horizon Telescope project, and it involved coordinating 8 radiotelescope facilities scattered across the globe, from Hawaii to Antarctica. In April 2017, all 8 telescopes simultaneously observed 2 targets: Sagittarius A star at the center of our galaxy, and an even more massive black hole at the center of a galaxy called Messier 87, located 55 million light-years away. The data collected during those observations amounted to 5 petabytes of information, so much data that it couldn't be transmitted over the internet. They had to physically ship hard drives to a central processing facility. It took 2 years of intensive analysis to convert that raw data into an image. And then, on April 10, 2019, the world saw something that had previously existed only in theoretical physics and science fiction: an actual photograph of a black hole. The image showed M87 star, the supermassive black hole at the center of Messier 87. It appeared as a glowing orange ring with a dark center, exactly as general relativity predicted it should look. The glowing ring was the accretion disk, superheated material orbiting the black hole at relativistic speeds. The dark center was the shadow of the event horizon, the point where the black hole's gravity is so strong that it bends the light around it, creating a silhouette against the bright background. That dark circle in the center of the image represents the event horizon of a black hole that weighs 6.5 billion times more than our Sun. It was the first time in human history that we'd actually seen one of these objects, and the image was simultaneously exactly what the theory predicted and utterly surreal to behold. Interestingly, the Event Horizon Telescope team initially planned to image Sagittarius A star first, since it's our own galactic black hole. But M87 star turned out to be an easier target despite being thousands of times farther away. Why? Because it's so much more massive. M87 star weighs about 1,500 times more than Sagittarius A star, which means it's physically larger and therefore easier to resolve, even at a greater distance. The Event Horizon Telescope did eventually produce an image of Sagittarius A star, released in May 2022, confirming that we could now directly observe the supermassive black hole right in our own cosmic backyard. These images represented a triumph of human ingenuity, international cooperation, and our fundamental desire to understand the universe. But they also opened up new questions. M87 star is enormous, weighing 6.5 billion solar masses, but it's not even close to the largest supermassive black hole we've discovered. Not by a long shot. As our telescopes improved throughout the late 20th and early 21st centuries, we began discovering supermassive black holes of truly staggering proportions. These weren't just millions of times more massive than the Sun. We were finding black holes with billions, tens of billions, even potentially over 100 billion solar masses. And this is where things start to break our intuition about scale. When we talk about stellar mass black holes, the ones formed from collapsed stars, we're usually talking about objects between 5 and 100 solar masses. Their event horizons are tiny, just a few kilometers to maybe 100 kilometers across. You could fit one inside a large city. But supermassive black holes are different. The event horizon of a black hole grows linearly with its mass. Double the mass, and you double the radius of the event horizon. This relationship is described by the Schwarzschild radius formula. The radius equals 2 times the gravitational constant times the mass, divided by the speed of light squared. For a black hole with the mass of our Sun, the Schwarzschild radius would be about 3 kilometers. For Sagittarius A star, at 4 million solar masses, the event horizon has a radius of about 12 million kilometers, roughly 17 times the radius of the Sun. That's already enormous, but remember, Sagittarius A star is actually one of the smaller supermassive black holes. Now let's talk about TON 618. At 6 billion solar masses, its event horizon has a radius of approximately 195 billion kilometers, or about 1,300 astronomical units. An astronomical unit is the distance from the Earth to the Sun, roughly 150 million kilometers. Neptune, the outermost planet in our solar system, orbits at about 30 AU from the Sun. The orbit of Neptune would fit inside the event horizon of TON 618 more than 40 times over. If you replace the Sun with TON 618, its event horizon would extend far beyond the Kuiper belt, beyond the scattered disk, even beyond the inner edge of the Oort cloud. Practically everything we consider part of the solar system would be inside this black hole's point of no return. And here's another way to think about it. Light travels at 300,000 kilometers per second. At that speed, light takes about 8 minutes to travel from the Sun to Earth. It takes about 4 hours for light to reach Neptune, but to cross the diameter of TON 618's event horizon, light would need nearly 11 days. 11 days of traveling at the fastest speed possible in the universe just to cross from one side to the other. These scales are so enormous that they start to lose meaning. Our brains didn't evolve to comprehend distances like this, but it's important to sit with just how incomprehensibly massive these objects are, because the existence of supermassive black holes raises some very uncomfortable questions. The first and most obvious is, how did they get so big? Black holes grow by consuming matter. When gas, dust, stars, or even other black holes fall past the event horizon, they add their mass to the black hole, making it larger. This seems straightforward enough, but there's a catch. There's a limit to how fast a black hole can grow, and that limit is set by the physics of accretion. When matter falls toward a black hole, it doesn't just drop straight in. It forms a swirling accretion disk, heating up due to friction and gravitational compression. This material becomes so hot that it emits intense radiation, including X-rays and gamma rays. This radiation creates an outward pressure that pushes against in-falling material. At a certain rate of accretion, the outward radiation pressure exactly balances the inward gravitational pull. This is called the Eddington limit, named after astronomer Arthur Eddington, who first described it. If a black hole tries to consume matter faster than the Eddington limit, the radiation pressure will simply blow the excess material away. For a black hole of a given mass, we can calculate its maximum growth rate based on the Eddington limit. And here's the problem. Even if a supermassive black hole has been feeding constantly at the Eddington limit since the very beginning of the universe, it shouldn't be as massive as some of the ones we observe. The universe is approximately 13.8 billion years old. The first stars probably formed a few 100 million years after the Big Bang. That means supermassive black holes have had, at most, about 13 billion years to grow. If you start with a stellar mass black hole of, say, 100 solar masses, and let it feed at the Eddington limit for 13 billion years, you can calculate how massive it would become using exponential growth equations. The result is impressive, but it's not 66 billion solar masses. It's not even close. To grow a black hole as massive as tau n 618 in the available time, you'd need to exceed the Eddington limit by a significant factor, which we don't have a clear mechanism for. Or you'd need to start with a much more massive seed black hole, something much larger than the remnant of a collapsed star. But where would those massive seed black holes come from? This is one of the great unsolved mysteries in astrophysics, and it's become even more pressing in recent years thanks to observations from the James Webb Space Telescope. JWST has been peering deeper into space, and therefore further back in time, than any previous telescope. And what it's finding is deeply puzzling. We're discovering massive quasars, powered by supermassive black holes weighing billions of solar masses in the very early universe, less than a billion years after the Big Bang. Some of these black holes appear to have formed within just 700 million years of the Big Bang. That's not enough time for them to have grown from stellar mass seeds, even under the most optimistic assumptions. Something else must be going on. Either black holes can grow much faster than we think under certain conditions, or they're starting from much more massive seeds than stellar remnants, or there's something fundamentally wrong with our understanding of the early universe. The classification of black holes by mass might seem straightforward at first glance, but like most things in astrophysics, it's more complicated than it appears. At the smallest end of the spectrum, we have stellar mass black holes, formed from the gravitational collapse of massive stars at the end of their lives. These typically range from about 5 solar masses up to around 100 solar masses, though the upper limit is somewhat fuzzy and depends on the details of stellar evolution. Their event horizons are relatively tiny by cosmic standards, ranging from about 15 kilometers in radius for a 5 solar mass black hole up to perhaps 300 kilometers for the most massive stellar black holes we've observed. To put that in perspective, you could fit the event horizon of a typical stellar mass black hole inside a large metropolitan area. Then we have what are called intermediate mass black holes, and this is where things get interesting, because we're not entirely sure these exist. The intermediate mass category is supposed to cover black holes between about 100 and 100,000 solar masses, bridging the gap between stellar mass and supermassive black holes. The problem is that we have very few confirmed detections of black holes in this mass range. We've found a handful of candidates, usually detected through gravitational waves when two smaller black holes merge to create something in the intermediate range, or through observations of unusual X-ray sources in dense star clusters. But for the most part, this mass range is conspicuously empty in our observations. It's like looking at a distribution of human heights and finding lots of people who are 5 feet tall, lots of people who are 6 feet tall, but almost nobody in between. It suggests there's something about the formation and evolution of black holes that preferentially creates either stellar mass or supermassive black holes, but not much in the middle. This missing middle is actually another piece of the puzzle when it comes to understanding how supermassive black holes form and grow. At the top end of the scale, we have supermassive black holes, generally defined as anything over about 100,000 solar masses, though in practice, most supermassive black holes we've discovered are millions or billions of times more massive than the Sun. And recently, astronomers have started using another term for the very largest black holes: ultramassive. There's no universally agreed upon boundary between supermassive and ultramassive, but it's often placed somewhere around 10 billion solar masses. These ultramassive black holes represent the absolute upper end of what we've observed, and they might also represent a physical limit to how large black holes can grow, though we're not entirely sure why such a limit would exist. Now, the event horizon of a black hole scales directly with its mass according to a beautifully simple relationship. The Schwarzschild radius, which is the radius of the event horizon for a non-rotating black hole, equals 2 times the gravitational constant times the mass, divided by the speed of light squared. Let's break down what this means in practical terms. For our Sun, if you somehow compressed all of its mass down into a black hole, which won't actually happen because the Sun isn't massive enough to collapse into a black hole, but if you did, the event horizon would have a radius of about 3 kilometers. That means you'd have to squeeze all the mass of the Sun, which is currently spread across a sphere with a radius of about 700,000 kilometers, down into a sphere with a radius of 3 kilometers. The density required to create a black hole is, to use a technical term, absolutely bonkers. For a stellar mass black hole of 10 solar masses, the event horizon radius would be about 30 kilometers. For 100 solar masses, about 300 kilometers. This linear relationship continues all the way up the mass scale. Sagittarius A star, at roughly 4 million solar masses, has an event horizon radius of about 12 million kilometers. That's roughly 17 times the radius of the Sun, or about 8% of the distance between the Earth and the Sun. M87 star, the black hole we famously photographed with the Event Horizon Telescope, weighs in at 6.5 billion solar masses and has an event horizon radius of approximately 19.5 billion kilometers, or about 130 astronomical units. That's more than 4 times the distance from the Sun to Neptune. If you placed M87 star at the center of our solar system, its event horizon would extend well past the orbits of all 8 planets, past Pluto, and deep into the Kuiper Belt. But let's talk about the really big ones. TOEN 618, currently the most massive black hole we've reliably measured, sits at 66 billion solar masses with an event horizon radius of about 195 billion kilometers, or 300 astronomical units. But there's another candidate that might be even larger, though the measurements are much more uncertain. At the center of a galaxy cluster known as Phoenix A, there appears to be a black hole with a mass somewhere between 60 and 100 billion solar masses. The uncertainty in this measurement is huge, which is why Tau 618 still holds the title as the largest confirmed supermassive black hole. But if the higher estimates for Phoenix A are correct, we're talking about an event horizon with a radius approaching 2,000 astronomical units. To put this in perspective, the nearest star to our Sun, Proxima Centauri, is about 270,000 astronomical units away. The event horizon of Phoenix A's black hole would cover less than 1% of the distance to the nearest star, which might make it sound small, but consider this. The Sun's gravitational influence, defined by its Hill sphere, extends out to about 2 astronomical units. Everything within that distance is gravitationally dominated by the Sun. The event horizon of Phoenix A's black hole would encompass a region about 1,000 times larger than the Sun's Hill sphere. You could fit 500 copies of our solar system out to the orbit of Neptune, inside that event horizon, and still have room left over. Now, here's something that breaks most people's intuition about black holes. Despite being incredibly massive, supermassive black holes are actually less dense than smaller black holes. Density is mass divided by volume, and volume increases with the cube of the radius. Since the event horizon radius grows linearly with mass, but volume grows with radius cubed, the average density inside the event horizon actually decreases as black holes get larger. A stellar mass black hole of 10 solar masses, with an event horizon radius of 30 kilometers, has an average density of about 2 times 10 to the power of 18 kilograms per cubic meter. That's incomprehensibly dense, about 2 billion metric tons per cubic centimeter. For comparison, the densest material on Earth, osmium, has a density of about 22 grams per cubic centimeter. But Sagittarius A star, at 4 million solar masses, has an average density inside its event horizon of about 5 million kilograms per cubic meter. That's denser than any material on Earth, still incredibly dense by terrestrial standards, but it's nearly 500 billion times less dense than the stellar mass black hole. And for something like Tau 618, the average density drops even further, to about 11 kilograms per cubic meter. That's less dense than air at sea level on Earth, which has a density of about 1.2 kilograms per cubic meter. Now, to be absolutely clear, this doesn't mean there's just air swirling around inside the event horizon of Tau 618. The mass is collapsed down to a singularity at the center, a point of infinite density where all the mass is concentrated and where our physics completely breaks down. We're talking about average density across the entire volume enclosed by the event horizon, which is a somewhat artificial measure but useful for comparison. The point is that you could, in theory, be inside the event horizon of an ultramassive black hole without experiencing extreme tidal forces, at least initially. With a stellar mass black hole, the tidal forces, the difference in gravitational pull between your head and your feet, become lethal long before you cross the event horizon. You'd be stretched into a long, thin strand of atoms, a process astrophysicists call spaghettification with only partial irony. But with an ultramassive black hole like Tau 618, the tidal forces at the event horizon are actually quite gentle. The gravitational field changes much more gradually across such an enormous distance. You could cross the event horizon and, for a while at least, not notice anything particularly dramatic. Of course, you'd still be doomed. Once you cross the event horizon, all paths through spacetime lead inward toward the singularity. There's no escaping, no turning back. And as you continue falling inward, getting closer to the singularity, the tidal forces would eventually ramp up and tear you apart just like they would with any other black hole. But the fact that you could potentially survive crossing the event horizon of an ultramassive black hole is one of those deeply weird consequences of general relativity. Now, let's talk about time, because this is where things get really strange. According to general relativity, time passes more slowly in stronger gravitational fields. This is called gravitational time dilation, and it's not just a theoretical prediction. It's been measured experimentally many times. GPS satellites have to account for time dilation because they're in a weaker gravitational field than we are on Earth's surface, and their clocks run slightly faster as a result. If they didn't correct for this, GPS navigation would accumulate errors of about 10 kilometers per day. Near a black hole, time dilation becomes extreme. If you were hovering just outside the event horizon of Sagittarius A star, somehow resisting the pull of gravity with an impossibly powerful rocket, time would pass much more slowly for you than for someone far away from the black hole. The closer you get to the event horizon, the more extreme this effect becomes. At the event horizon itself, time dilation becomes infinite. From the perspective of someone far away, watching you approach the event horizon, you would appear to slow down, moving more and more sluggishly, your clock ticking slower and slower, until you freeze at the event horizon, never quite crossing it. You'd appear to fade away as your light becomes increasingly red-shifted, stretched to longer and longer wavelengths by the extreme curvature of space-time. But from your perspective, falling toward the black hole, nothing special happens at the event horizon. You'd cross it in a finite amount of your own time, even though an outside observer would never see you cross. The strength of gravitational time dilation depends on how close you are to the Schwarzschild radius relative to the mass of the black hole. For a stellar mass black hole, time dilation effects become significant only when you're very close to the event horizon within a few kilometers. But for a supermassive black hole, because the event horizon is so much larger, time dilation effects spread out over a much vaster region of space. Near M87 star, if you were orbiting just outside the event horizon at the innermost stable circular orbit, time would be passing at roughly 58% of the rate it passes far from the black hole. 1 hour for you would correspond to about 1.7 hours for someone far away. Near TON 618, at the innermost stable, circular orbit, time dilation would be even more extreme due to the sheer scale of the space-time curvature. Now, most supermassive black holes aren't just sitting there quietly in the centers of galaxies. Many of them are actively feeding, consuming vast amounts of matter from their surroundings. This feeding process is one of the most energetically violent phenomena in the universe, and it's responsible for some of the brightest objects we can observe. When matter falls toward a black hole, it doesn't fall straight in. Due to conservation of angular momentum, the same principle that makes a figure skater spin faster when they pull their arms in, the infalling matter forms a rotating disk called an accretion disk. As this matter spirals inward, it collides with other material in the disk, generating friction. This friction converts the gravitational potential energy of the infalling matter into heat, and the temperatures reached in these accretion disks are extraordinary. In the inner regions of an accretion disk around a supermassive black hole, temperatures can reach 10 million degrees Kelvin or higher. At these temperatures, the material emits intense radiation across the electromagnetic spectrum, from radio waves all the way up to X-rays and gamma rays. The accretion disk around a supermassive black hole can be extraordinarily bright. sometimes outshining the entire galaxy that hosts it. These exceptionally bright accretion disks, when they're pointed roughly in our direction, are what we call quasars. The term quasar is short for quasi-stellar object, so named because they appear point-like in optical telescopes, similar to stars, but they're far too bright to be stars. A typical large galaxy contains somewhere between 100 and 400 billion stars. A bright quasar can emit more light than all of those stars combined. Let that sink in for a moment. A region of space, just a few light days across, containing nothing but a black hole and the material falling into it, can outshine 200 billion stars. The most luminous quasars we've observed emit energy at a rate of about 10 to the power of 41 watts. For comparison, our Sun emits about 4 times 10 to the power of 26 watts. These quasars are about 25 trillion times more luminous than the Sun. If you replaced the Sun with one of these quasars, even though the quasar is much farther away, at the center of the galaxy 27,000 light-years from Earth, it would still appear about 200 times brighter in our sky than the Sun does now. You could read by quasar light at midnight. The efficiency of this energy conversion is remarkable. When matter falls into a black hole, it converts some of its rest mass into energy according to Einstein's famous equation E equals mc squared. The efficiency of this conversion in an accretion disk can be around 10% for a rapidly spinning black hole, meaning 10% of the infalling mass gets converted to radiated energy. For comparison, nuclear fusion in the core of the Sun converts about 0.7% of mass to energy. Black hole accretion is more than 10 times more efficient than the nuclear fusion that powers stars. This is why supermassive black holes can be so bright despite being relatively compact. But the accretion disk isn't the only way that supermassive black holes announce their presence. Many of them also produce jets, narrow beams of particles and radiation that shoot out from the poles of the black hole at close to the speed of light. These jets are among the most impressive phenomena in all of astrophysics. The jet emanating from M87 star, the black hole we photographed with the Event Horizon Telescope, extends for about 5,000 light-years into space. That's roughly the distance from Earth to the center of our galaxy. This jet is visible in radio wavelengths, glowing with synchrotron radiation as relativistic electrons spiral around magnetic field lines. But some jets extend even farther. The jets from certain radio galaxies can reach lengths of millions of light-years, spanning the distance between multiple galaxies. The physical mechanism that produces these jets is still not fully understood, though we have a general picture. It involves the interaction between the accretion disk, the black hole's spin, and powerful magnetic fields that get wound up and concentrated by the rotating material. These magnetic fields can channel some of the infalling matter into narrow beams that shoot out along the black hole's rotation axis at relativistic speeds. The particles in these jets are moving so fast, often at more than 99% of the speed of light, that relativistic effects become important. One consequence is that the jet appears brighter when it's pointed toward us due to something called relativistic beaming. The radiation from particles moving toward us gets compressed and amplified, while radiation from particles moving away gets stretched out and dimmed. When a jet is pointed almost directly at Earth, we call it a blazar, and these are some of the most variable and energetic sources in the sky. The fact that supermassive black holes can launch jets of material spanning millions of light-years is itself remarkable. But it also tells us something important about their role in the universe. These jets carry enormous amounts of energy out into the surrounding space, heating the gas in galaxy clusters, stirring up turbulence, and even affecting the rate at which new stars can form in nearby galaxies. Supermassive black holes aren't just passive inhabitants of galactic centers. They actively shape the evolution of their host galaxies. Observing supermassive black holes is challenging for several reasons. First, as the name suggests, they're black. The event horizon itself emits no light. We can only observe them indirectly through their effects on surrounding matter, whether that's stars orbiting nearby, hot gas in an accretion disk, or jets of material shooting into space. Second, even though supermassive black holes are massive, they're also very far away and therefore appear tiny in the sky. As mentioned earlier, Sagittarius A star would appear smaller than an orange on the surface of the Moon if we could see it directly. It took a telescope the effective size of the entire Earth to resolve it. Third, for the most distant supermassive black holes, ones that are billions of light years away, we're not just observing them as they are now. We're seeing them as they were billions of years ago, when the light now reaching us first left them. This light has been traveling through expanding space for so long that it's been stretched to much longer wavelengths, red-shifted by the expansion of the universe. This makes distant quasars appear redder and dimmer than they would if they were nearby. Despite these challenges, we've developed several methods for detecting and measuring supermassive black holes. The most direct method, and the one that gave us the first definitive proof of Sagittarius A star, is to observe the motion of stars or gas clouds orbiting near the galactic center. By tracking these objects over time and mapping their orbits, we can use Kepler's laws to calculate the mass of whatever they're orbiting. This method works well for relatively nearby galaxies, where we can resolve individual stars or gas clouds, but it becomes impractical for galaxies millions or billions of light years away. For more distant supermassive black holes, we rely on other techniques. If the black hole is actively accreting matter, and therefore bright as a quasar or active galactic nucleus, we can observe the radiation from the accretion disk. The luminosity and spectrum of this radiation give us clues about the mass of the black hole, though these estimates are less precise than direct orbital measurements. Another technique involves measuring the width of emission lines in the spectrum of light from the accretion disk. The material in the accretion disk is moving very fast, orbiting at thousands of kilometers per second. Some of this material is moving toward us, and some is moving away. This motion causes the spectral lines to be Doppler shifted, broadened by the range of velocities present. The amount of broadening tells us how fast the material is moving, which in turn tells us about the strength of the gravitational field, which depends on the mass of the black hole. This method, called reverberation mapping, has been used to estimate the masses of hundreds of supermassive black holes in distant galaxies. We can also detect supermassive black holes through their gravitational effects on light itself. When light from a distant object passes near a massive foreground object like a galaxy or black hole, the path of the light gets bent by the curvature of spacetime. This is called gravitational lensing, and it can create multiple distorted images of the background object, or even form complete rings called Einstein rings. By analyzing the pattern of lensing, we can infer the mass of the foreground object, including any central supermassive black hole. And then there are gravitational waves. When two supermassive black holes orbit each other and eventually merge, they produce ripples in spacetime that propagate outward at the speed of light. These gravitational waves carry information about the masses of the merging black holes and the properties of the final merged black hole. The LIGO and Virgo detectors have revolutionized astronomy by detecting gravitational waves from merging stellar mass black holes. But these detectors aren't sensitive to the much lower frequency gravitational waves produced by merging supermassive black holes. For that, we'll need future space-based detectors like LISA, the Laser Interferometer Space Antenna, which is planned for launch in the 2030s. LIAS should be able to detect the mergers of supermassive black holes across the entire observable universe, opening a completely new window onto these cosmic giants. Let's take a tour of the cosmos and visit some of the most massive black holes we've discovered, because once you start looking at the actual numbers, the scale of these objects becomes almost impossible to process. We'll start close to home with Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. At approximately 4 million solar masses, it's actually one of the smaller supermassive black holes we know of, which should tell you something about just how extreme the others are. Sagittarius A star sits roughly 27,000 light-years from Earth in the direction of the constellation Sagittarius, hidden behind vast clouds of dust and gas that make it invisible to optical telescopes. Its event horizon has a diameter of about 24 million kilometers, which is roughly 17 times the diameter of the Sun. If you placed Sagittarius A star at the center of our solar system, its event horizon would fit comfortably inside the orbit of Mercury, which orbits at an average distance of about 58 million kilometers from the Sun. But the gravitational influence of Sagittarius A star extends far beyond its event horizon. The region around it is populated by stars moving at absolutely extraordinary speeds. The star S2, which we mentioned earlier, orbits Sagittarius A star with a period of about 16 years. At its closest approach, called periapsis, S2 comes within about 17 light-hours of the black hole. That's roughly 120 times the distance from the Earth to the Sun, and at that point it's traveling at almost 5,000 kilometers per second. That's nearly 2% of the speed of light. Imagine something with the mass of our Sun, which would have a volume large enough to fit over 1 million Earths inside it, moving at 2% of light speed. The kinetic energy involved is almost incomprehensible. There are dozens of other stars in tight orbits around Sagittarius A star, some even closer and faster than S2. These stars are designated with the letter S, followed by a number, and watching them dance around an invisible point in space over the course of years and decades is what allowed astronomers to definitively prove that Sagittarius A star exists, and to measure its mass with extraordinary precision. Right now, Sagittarius A star is relatively quiet. It's not currently consuming large amounts of matter, so it's not particularly bright compared to some other supermassive black holes. But that hasn't always been the case. There's evidence that Sagittarius A star was much more active in the relatively recent past, astronomically speaking. In 2010, astronomers discovered enormous bubble-like structures extending above and below the galactic plane, stretching for about 25,000 light-years in each direction. These structures, called the Fermi bubbles after the Fermi gamma-ray space telescope that discovered them, appear to be the remnants of a massive outburst from Sagittarius A star that occurred somewhere between 2 and 4 million years ago. During this outburst, Sagittarius A star likely had a bright accretion disk and was ejecting jets of material perpendicular to the galactic plane. The energy required to create structures as large as the Fermi bubbles is staggering, equivalent to the energy released by about 100,000 supernovae. Our galaxy's central black hole may be quiet now, but it has a violent past. and there's no reason to think it won't become active again in the future. Now, let's jump to a galaxy far, far away. Messier 87, also known as M87 or Virgo A, is a giant elliptical galaxy located about 55 million light-years from Earth in the constellation Virgo. It's one of the largest and most massive galaxies in the relatively nearby universe, containing several trillion stars compared to the few hundred billion in the Milky Way. And at its center sits M87 star, the supermassive black hole that became famous in 2019 when the Event Horizon Telescope captured the first ever direct image of a black hole. M87 star weighs approximately 6.5 billion solar masses, making it about 1,500 times more massive than Sagittarius A star. Its event horizon has a diameter of about 39 billion kilometers, or roughly 260 astronomical units. That's more than 8 times the distance from the Sun to Neptune. If you replaced our Sun with M87 star, its event horizon would extend past the orbits of all 8 planets, past Pluto, and deep into the Kuiper Belt, swallowing countless icy bodies that orbit in the outer reaches of the solar system. But the event horizon is just the beginning of M87 star's sphere of influence. The famous image captured by the Event Horizon Telescope shows a glowing orange ring with a dark center. That ring is radiation from the accretion disk, material orbiting the black hole at relativistic speeds, heated to billions of degrees by friction and compression. The ring appears brighter on one side than the other due to relativistic beaming. The material on one side of the disk is moving toward us, and its radiation is amplified, while the material on the other side is moving away, and its radiation is diminished. The dark center of the image is larger than the event horizon itself. It's the black hole's shadow, the region where the gravitational field is so strong that it bends light into highly curved paths. Some light rays that would otherwise reach us get captured by the black hole or deflected away, creating a shadow that's about 2.5 times larger than the event horizon. This shadow spans about 100 billion kilometers across, roughly the distance light travels in 4 days. M87 star is actively feeding, consuming matter from its surroundings, and it's also producing one of the most spectacular jets ever observed. This jet, which appears as a bright streak in radio telescope images, extends for approximately 5,000 light-years from the black hole. To give you a sense of scale, that's about the distance from Earth to a point roughly 1/5 of the way across the Milky Way. The jet consists of plasma, superheated ionized gas, traveling at close to the speed of light. Electrons spiraling around magnetic field lines in the jet emit synchrotron radiation, making the jet glow in radio wavelengths. The total power output of this jet is estimated at around 10 to the 42 watts, which is equivalent to the energy output of about 2 trillion suns. The jet from M87 star extends far beyond the 5,000 light-year visible structure. At larger scales, it creates enormous lobes of radio emission that span hundreds of thousands of light-years, interacting with the hot gas that fills the space between galaxies in the Virgo cluster. These jets aren't just impressive to look at. They have real consequences for the evolution of M87 and its surroundings. The energy pumped out by the jet heats the surrounding gas, preventing it from cooling and collapsing to form new stars. This feedback mechanism, where the supermassive black hole regulates star formation in its host galaxy, is thought to be one of the reasons why giant elliptical galaxies like M87 are often dead or dying, with very little ongoing star formation despite containing enormous amounts of gas. Now, let's talk about IC 1101, one of the largest known galaxies in the universe. Located over 1 billion light-years away at the center of the Abell 2029 galaxy cluster, IC 1101 is a supergiant elliptical galaxy that dwarfs the Milky Way. While our galaxy is about 100,000 light-years across, IC 1101 spans approximately 6 million light-years, making it one of the largest known galaxies by diameter. It contains an estimated 100 trillion stars, hundreds of times more than the Milky Way. And at its center, naturally, sits a supermassive black hole. The mass estimates for IC 1101's central black hole vary widely depending on the method used and range from about 40 billion to over 100 billion solar masses. The uncertainty here is enormous, which is common when dealing with such distant objects. At the lower end of the estimates, 40 billion solar masses, the event horizon would have a diameter of about 475 billion kilometers, or roughly 3,200 astronomical units. That's more than 100 times the distance from the Sun to Neptune. At the upper end of the estimates, if the black hole is truly around 100 billion solar masses, its event horizon would span approximately 1,200 billion kilometers, or about 8,000 astronomical units. To put this in perspective, the Voyager 1 spacecraft, humanity's most distant emissary, launched in 1977 and is currently about 160 astronomical units from the Sun. It would take Voyager 1 roughly 50 times longer than it's already been traveling, assuming it could maintain its current velocity, to cross from one side of IC 1101's event horizon to the other, and that's using the lower mass estimate. The difficulty in pinning down the mass of such distant supermassive black holes highlights one of the challenges in studying these objects. At a distance of over 1 billion light-years, we can't resolve individual stars orbiting the black hole the way we can with Sagittarius A star. We have to rely on more indirect methods, like measuring the velocity dispersion of stars in the galactic core, or analyzing the light from the accretion disk if the black hole is actively feeding. These methods are less precise and can give results that differ by factors of 2 or 3. But even with these uncertainties, it's clear that IC 1101 hosts one of the most massive black holes known. Let's move on to one of the current record holders. Taon 6018 is a hyperluminous quasar located approximately 10.4 billion light-years from Earth. When we observe Taon 618, we're seeing it as it was 10.4 billion years ago, when the universe was only about 3 billion years old, less than a quarter of its current age. Despite this enormous distance, Taon 618 is one of the brightest objects in the sky when observed in certain wavelengths. It's so luminous that it has an absolute magnitude of -30.7, which means that if you placed it at a standard distance of 10 parsecs, about 33 light-years, it would appear in the sky as bright as our Sun does from Earth. Actually, it would be even brighter, outshining the Sun by a factor of several hundred. The central black hole of Taon 618 has a mass of approximately 66 billion solar masses, making it one of the most massive black holes ever measured with any confidence. Its event horizon has a diameter of about 390 billion kilometers, or roughly 2,600 astronomical units. This is where comparisons to the solar system start to lose their impact because the numbers become so large they stop meaning anything. But let's try anyway. The Oort cloud, a vast, spherical shell of icy bodies that surrounds the solar system, is thought to extend from about 2,000 to 100,000 astronomical units from the Sun. The event horizon of Taon 618 would extend well into the inner Oort cloud. Objects that we consider to be barely clinging to the Sun's gravitational influence, making lazy orbits that take millions of years to complete, would be inside the point of no return around tau n 618. If light takes about 8 minutes to travel from the Sun to Earth, it takes light nearly 5.5 days to travel from one side of TON 618's event horizon to the other. If you were somehow standing at one edge of the event horizon and shining a flashlight across to the other side, it would take almost 11 days for the light to make the round trip. The accretion disk around tau n 618 is pumping out energy at an almost incomprehensible rate. The bolometric luminosity, that's the total energy output across all wavelengths, is estimated at about 4 times 10 to the power of 40 watts. That's equivalent to the combined output of approximately 140 trillion suns, or about 350 times the luminosity of the entire Milky Way galaxy. All of this energy is being generated in a region much, much smaller than the Milky Way, which is about 100,000 light-years across. The accretion disk of TON 618 is probably a few light weeks across at most. To sustain this level of luminosity, TON 618 is consuming matter at a rate of several hundred solar masses per year. Every year, this black hole devours the equivalent of hundreds of stars, converting about 10% of that mass directly into radiated energy. It's essentially a machine for turning matter into light, and it's one of the most efficient and powerful machines in the entire universe. But TON 618 might not hold the record for long. There's another candidate, and this one is even more massive, though the measurements are significantly more uncertain. At the center of the galaxy cluster, Abel 85, there's a massive elliptical galaxy called Holmberg 15A. And at the center of Holmberg 15A, there appears to be an ultramassive black hole. Early estimates published in the late 2010s suggested this black hole could have a mass as high as 170 billion solar masses. If that were accurate, it would absolutely shatter the record held by TON 618. However, subsequent reanalysis of the data suggested the mass was likely overestimated, and more recent estimates place it somewhere between 40 and 310 billion solar masses. That's an enormous range of uncertainty, which tells you just how difficult these measurements are. But even taking the lower end of that range, 40 billion solar masses, this is still an extraordinarily massive object. And then there's Phoenix A. The galaxy, Phoenix A, also known as Holmberg 15A. Wait, no, that's a different galaxy. Naming in astronomy is a mess. Let me start over. Phoenix A, the brightest galaxy in the Phoenix cluster, contains what might be one of the largest black holes ever discovered. Located about 5.8 billion light-years away, Phoenix A is an enormous elliptical galaxy at the center of a galaxy cluster. The central black hole has been estimated to have a mass of around 100 billion solar masses, though like many of these extreme measurements, there's substantial uncertainty. If this estimate is correct, the event horizon would have a diameter of about 780 billion kilometers, or roughly 5,200 astronomical units. What makes Phoenix A particularly interesting isn't just the mass of its central black hole, but the enormous radio jets it produces. These jets extend for millions of light-years into space, making them some of the longest jets ever observed. The total length from one end of the jet structure to the other is approximately 5.2 million light-years. To put that in perspective, the distance from the Milky Way to the Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years. The jets from Phoenix A span more than twice that distance. The energy required to create and maintain such enormous structures is staggering, and it speaks to the incredible power of supermassive black holes to influence their surroundings on truly cosmic scales. Now, you might be wondering, Is there a limit to how massive a black hole can get? And the answer is, we're not entirely sure, but there probably is. As a black hole grows, it becomes increasingly difficult for it to continue growing. The Eddington limit, which we discussed earlier, sets a maximum rate at which a black hole can accrete matter. Push beyond that limit, and radiation pressure blows away the infalling material before it can cross the event horizon. Additionally, as a galaxy evolves and its central black hole grows, feedback mechanisms kick in. The energy output from the accretion disk and jets heats the surrounding gas, preventing it from cooling and falling into the black hole. Over time, this feedback can starve the black hole, cutting off its food supply. There may also be dynamical constraints. In the cores of galaxies, stars are constantly passing by the central black hole, and occasionally one gets too close and is captured. But as the black hole grows more massive, its gravitational influence extends farther out, and, paradoxically, it becomes less efficient at capturing nearby stars. The larger event horizon doesn't necessarily mean more stars fall in, because the density of stars in the galactic core is finite, and there are only so many stars in orbits that will intersect with the black hole. Some theoretical models suggest there might be a practical upper limit to black hole masses somewhere around 50 to 100 billion solar masses, though this is far from settled science. The fact that we have discovered black holes pushing up against this theoretical limit, and possibly exceeding it, suggests that either the limit is higher than we think, or our models of black hole growth need refinement. There's also the question of whether we've actually found the largest black holes, or whether there are even more massive ones out there waiting to be discovered. Our surveys of the universe are incomplete, and we tend to find the objects that are easiest to observe, which means bright quasars at large distances or nearby, galaxies where we can track stellar orbits. There could be ultramassive black holes in galaxies that aren't actively feeding and therefore aren't bright, and we simply haven't found them yet because they're not announcing their presence. As our telescopes improve and our surveys become more complete, we may well discover black holes that make TOEN 618 look small by comparison. Or we might find that TOEN 618 really is near the upper limit, and that tells us something fundamental about how black holes and galaxies co-evolve. One thing that becomes clear when you look at this rogues' gallery of supermassive black holes is just how common they are. We've found them in virtually every large galaxy we've examined closely enough. The Milky Way has one. Andromeda has one that's about twice as massive as ours, roughly 100 million solar masses. The Sombrero Galaxy has one around 1 billion solar masses. It seems to be a universal feature of galaxy formation that a supermassive black hole ends up at the center. In fact, there's a remarkably tight correlation between the mass of a galaxy's central black hole and the mass of its central bulge, the dense spheroidal region of stars surrounding the galactic core. This relationship suggests that the growth of the central black hole and the growth of the galaxy are intimately connected, that they're not independent processes but rather coupled together through feedback mechanisms. The black hole feeds on gas falling toward the galactic center, grows more massive, pumps more energy into its surroundings through radiation and jets, which affects how and where stars form in the galaxy, which in turn affects how much gas continues to fall toward the center. It's a complex dance that plays out over billions of years, and we're only beginning to understand the details. The discovery of supermassive black holes in the early universe has created one of the most perplexing problems in modern astrophysics. The issue isn't just that these black holes exist, it's that they exist far too early in cosmic history, and they're far too massive for us to explain with our current understanding of how black holes form and grow. Let me paint you a picture of the problem. The Big Bang occurred approximately 13.8 billion years ago. For the first few hundred million years after the Big Bang, the universe was a very different place. It was smaller, denser, hotter, and filled with neutral hydrogen gas that was essentially opaque to light. There were no stars, no galaxies, no black holes, just this fog of hydrogen atoms slowly spreading out as the universe expanded. This period is called the Cosmic Dark Ages, and it lasted until the first stars began to form. These first stars, called population 3 stars, were very different from stars today. They formed from pristine hydrogen and helium with essentially no heavier elements, because heavier elements are created inside stars and scattered into space when stars die, and at this point, no stars had lived and died yet. These population 3 stars are thought to have been absolutely enormous, perhaps 100 to 1,000 times the mass of the Sun, burning incredibly hot and bright but living very short lives, maybe only a few million years. When these massive stars exhausted their fuel, they would have collapsed and likely formed black holes, perhaps with masses of 50 to 500 solar masses or even higher. These stellar remnants could serve as seeds for supermassive black holes. A black hole with a mass of a few hundred suns forms in the early universe, begins accreting surrounding gas, slowly grows larger, and over billions of years, through continuous feeding and occasional mergers with other black holes, it eventually becomes the supermassive black holes we observe today. That's the basic story, and for a long time it seemed reasonable. But then we started finding problems with the timeline. In 2001, astronomers discovered a quasar designated SDSS JUN30 plus 0524, located at a redshift that corresponds to when the universe was only about 900 million years old. The black hole powering this quasar had a mass of approximately 2 billion solar masses. That was surprising, but not completely shocking. Over the next 2 decades, as our telescopes improved, we kept finding more of these early quasars, and they kept pushing back to earlier and earlier times. Then, the James Webb Space Telescope launched in late 2021, and things got really interesting. JWST was specifically designed to observe the early universe with unprecedented sensitivity, and it has absolutely delivered on that promise. Within its first year of operations, JWST discovered multiple quasars in the universe when it was less than 800 million years old. Some of these quasars are powered by black holes with masses of several billion solar masses. The current record holder is a quasar that JWST observed from when the universe was only about 700 million years old, and it appears to be powered by a black hole with a mass somewhere in the range of 10 million to possibly over a billion solar masses, depending on which analysis you trust. Now, 700 million years might sound like a long time, and it is by human standards. But in cosmic terms, when you're trying to build a billion solar mass black hole, 700 million years is not very much time at all. Let's do some math to see why this is such a problem. Suppose you start with a seed black hole formed from one of those early population 3 stars, say 200 solar masses. This black hole begins accreting gas from its surroundings. As we discussed earlier, there's a limit to how fast it can grow called the Eddington limit. When a black hole accretes matter, the infalling material heats up and radiates energy. If too much matter tries to fall in at once, the radiation pressure from all that energy being released pushes the excess material away. The Eddington limit gives you the maximum accretion rate at which radiation pressure exactly balances gravitational attraction. For a black hole accreting at the Eddington limit continuously, its mass grows exponentially with a characteristic timescale called the salpeter time, which is about 45 million years. This means that if a black hole feeds at the Eddington limit without interruption, its mass increases by a factor of E, that's 2.718, approximately every 45 million years. Let's be optimistic and assume our 200 solar mass seed black hole manages to feed at exactly the Eddington limit constantly for 700 million years with no breaks. That's 700 divided by 45, which is about 15.5 salpeter times. Starting with 200 solar masses and growing by a factor of E every 45 million years for 15.5 salpeter times gives you 200 times EI to the power of 15.5, which works out to approximately 1 billion solar masses. So, in the absolute best-case scenario, where everything goes perfectly, and the black hole feeds at the maximum possible rate without interruption for 700 million years, you can just barely grow a billion solar mass black hole from a 200 solar mass seed. But here's the problem. This scenario is wildly optimistic. Black holes don't actually feed continuously at the Eddington limit. There are interruptions. Sometimes there's not enough gas nearby to accrete. Sometimes feedback from the black hole itself heats or blows away the surrounding gas, cutting off the food supply. Sometimes the gas has too much angular momentum and can't fall straight in. Real black holes probably spend significant periods of time accreting at well below the Eddington limit, or not accreting at all. Additionally, we're assuming that you can start with a 200 solar mass seed black hole just 700 million years after the Big Bang. But remember, you first need to form population 3 stars, wait for them to live out their short but non-zero lifetimes, maybe a few million years, and then collapse into black holes. So you're not really starting at time zero. You're starting maybe 100 million years after the Big Bang at the earliest, which leaves you only 600 million years to do all this growth. And there's another complication. Those population 3 stars are expected to form individually or in small groups, scattered across vast regions of space. How do their remnant black holes end up at the centers of galaxies where we observe these massive quasars? Galaxies themselves take time to assemble. In the early universe, structure forms hierarchically, with smaller clumps of matter gradually merging together to build larger structures. The first galaxies were probably quite small, perhaps just a few million to tens of millions of solar masses in total, not the billions or trillions of solar masses we see in large galaxies today. These proto-galaxies would then merge together over time, building larger and larger structures. If you have a black hole in each of these small proto-galaxies, then when the galaxies merge, their black holes would eventually sink to the center and merge as well, creating a larger black hole. This process of hierarchical growth through mergers can help, but it still takes time for the mergers to happen and for the black holes to spiral together. Some models suggest this hierarchical growth might not be fast enough to produce billion solar mass black holes in the required time frame. So we're left with a puzzle. We observe supermassive black holes that shouldn't exist yet, at least not according to our standard models. This has forced astrophysicists to consider alternative scenarios for how these black holes might have formed and grown so quickly. One possibility is that the seed black holes were much more massive than the few hundred solar masses we'd expect from population 3 stars. If you could somehow start with a seed black hole of 10,000 or even 100,000 solar masses, you'd have a much easier time growing it to 1 billion solar masses in the available time. But where would such massive seeds come from? One idea is called direct collapse. Under certain specific conditions in the early universe, a large cloud of gas might collapse directly into a black hole without ever forming a star first. This could happen if the gas cloud is massive enough and hot enough that it can't fragment into smaller pieces, which is what normally happens during star formation. If the gas stays in one coherent lump and collapses all at once, it might be able to avoid the intermediate step of forming a star and collapse directly to a black hole with a mass of perhaps 10,000 to 100,000 solar masses right from the start. The problem is that the conditions required for direct collapse are quite specific and might not have been very common in the early universe. You need a region with lots of gas but very little dust and metals, because metals help the gas cool down, and if the gas cools too much, it will fragment. You also need a source of radiation to keep the hydrogen atoms ionized, preventing them from forming molecules that would also cool the gas. Some models suggest that these conditions might have occurred in rare regions near the first galaxies, but it's unclear whether direct collapse was common enough to explain all the supermassive black holes we observe in the early universe. Another possibility is primordial black holes. What if some black holes didn't form from stars at all, but instead formed directly in the extreme conditions of the Big Bang itself? In the first fraction of a second after the Big Bang, there were enormous density fluctuations in the expanding universe. If any of these fluctuations were large enough, they might have collapsed directly into black holes while the universe was still extremely young. These primordial black holes could have a wide range of masses, potentially including very massive ones that could serve as seeds for supermassive black holes. The problem with primordial black holes is that we have very little direct evidence that they exist. They remain a theoretical possibility, and while they could solve some problems in astrophysics, including the early growth of supermassive black holes and possibly even contributing to dark matter, we haven't definitively detected any. Searches for primordial black holes through gravitational lensing and other methods have mostly come up empty, suggesting that if they exist, they're not particularly common. Yet another idea involves super-Eddington accretion. What if, under the right conditions, black holes can actually exceed the Eddington limit and accrete matter faster than we thought possible? There are some theoretical models suggesting this might work if the accretion flow is optically thick, meaning the inflowing material is so dense that radiation has trouble escaping. In this scenario, radiation gets trapped in the infalling material and is carried across the event horizon rather than pushing material away. This could allow for brief periods of very rapid growth, potentially speeding up the timeline for building supermassive black holes. Some computer simulations of black hole growth in the early universe have found that super-Eddington accretion might occur more often than previously thought, especially during galaxy mergers when large amounts of gas get funneled toward the central black hole. However, it's unclear whether super-Eddington accretion can be sustained long enough to make a significant difference in the growth timeline. There's also the possibility that we're simply underestimating the efficiency of the hierarchical growth process. Maybe black hole mergers were more common in the early universe than we think, or maybe the first black holes formed in especially dense environments where they had easy access to large amounts of gas. Some recent simulations have suggested that if you fine-tune the conditions just right, you might be able to grow billion solar mass black holes fast enough to match the observations. But this fine-tuning is somewhat unsatisfying because it requires a lot of things to go right, and it's not clear why the early universe would preferentially produce these ideal conditions. And then there's the more radical possibility that our understanding of physics in the early universe is incomplete or wrong. Maybe the Eddington limit doesn't apply the same way in the extreme conditions of the first billion years. Maybe gravity worked slightly differently when the universe was denser and hotter. Maybe there's some aspect of black hole formation or growth that we're missing entirely. This is the kind of explanation that physicists are generally reluctant to invoke because it opens the door to all sorts of speculation. But it's worth keeping in mind that our understanding of the early universe is based largely on extrapolating our current physics backward in time. If there are new physical processes or phenomena that only become important in extreme conditions, we might not know about them yet. The James Webb Space Telescope is continuing to push our observations deeper into the early universe, and with each new discovery, the tension between theory and observation grows. We're now finding not just a few anomalous supermassive black holes in the early universe, but many of them, which suggests this isn't just a statistical fluke or a measurement error. These objects really exist, and they're forcing us to reconsider our models of the early universe. One particularly intriguing discovery from JWST is that some of these early quasars appear to be overly massive relative to their host galaxies. In the local universe, there's a tight correlation between the mass of a galaxy's central black hole and the mass of its stellar bulge, with the black hole typically being about 0.1 to 0.2% of the bulge mass. But some of these early quasars seem to have black holes that are a much larger fraction of their galaxy's total mass, sometimes a few percent or even higher. This suggests that in the early universe, black holes might have grown faster than their host galaxies, which is the opposite of what happens later in cosmic history. This could be a clue to understanding how these massive black holes formed so quickly. Perhaps in the early universe, conditions were such that black holes had easier access to fuel and could grow rapidly, and only later did feedback mechanisms become efficient enough to regulate their growth and establish the tight correlation we see today. Another angle on this problem comes from gravitational wave astronomy. When the LISA space-based gravitational wave detector launches in the 2030s, it will be sensitive to the mergers of supermassive black holes. By detecting these merger events across cosmic time, we'll be able to directly observe how supermassive black holes grow through mergers and piece together a more complete picture of their evolution. If we detect numerous mergers of intermediate mass black holes in the early universe, that would support the hierarchical growth model. If we don't, that might point toward direct collapse or some other mechanism. The seeds of supermassive black holes, whether they're stellar remnants, direct collapse black holes, primordial black holes, or something else entirely, remain one of the great mysteries of modern astrophysics. Every new observation seems to deepen the mystery rather than solve it. The black holes we're finding in the early universe are too massive, too common, and too well established to easily fit into our theoretical frameworks. Something is missing from our models, and figuring out what that something is will likely require a combination of better observations, more sophisticated simulations, and possibly some genuinely new physics. There's also a philosophical dimension to this problem that's worth considering. The supermassive black holes we observe in the early universe existed when the universe was less than 5% of its current age. They were already billions of times more massive than the Sun, when the cosmos was still in its infancy. These objects are among the first large-scale structures to form after the Big Bang, and their rapid growth suggests that the early universe was a much more dynamic and violent place than we typically imagine. The cosmic dark ages might have been dark in the sense that there were no stars yet, but they were also the era when the seeds of future galaxies and the massive black holes at their centers were being planted. Understanding how these seeds formed and grew isn't just an academic exercise. It's fundamental to understanding how structure formed in the universe, how galaxies came to be, and ultimately how we came to be. The matter that makes up our bodies was forged inside stars, but those stars formed within galaxies, and those galaxies were shaped by the supermassive black holes at their centers. The timeline crisis posed by early supermassive black holes isn't just about black holes. It's about the entire history of cosmic structure formation, and solving it will require us to rethink some of our most basic assumptions about how the universe evolved from a nearly smooth sea of hydrogen gas to the rich tapestry of galaxies, stars, and planets we see today. Some researchers have proposed that we might be looking at this problem from the wrong direction. Instead of asking how black holes grew so fast, maybe we should be asking whether they needed to grow at all. What if some supermassive black holes, or at least their seeds, were present from the very beginning, formed in the Big Bang itself? This would completely sidestep the growth problem, because you're not building up from small stellar mass seeds, but rather starting with something already massive. The challenge with this idea is reconciling it with our observations of the Big Bang and the early universe, which don't show obvious signs of massive black holes forming directly. But, as JWST continues to observe the early universe and potentially push back to even earlier times, we might find evidence that forces us to seriously consider this possibility. Another aspect of the problem involves the role of dark matter. Dark matter makes up about 85% of all matter in the universe, and it plays a crucial role in structure formation because its gravity pulls ordinary matter together into clumps that eventually become galaxies. Some models suggest that the distribution and properties of dark matter in the early universe might have influenced how quickly black holes could form and grow. If dark matter was distributed differently than we think, or if it interacted with ordinary matter in ways we don't fully understand, that could potentially speed up black hole growth. There are even more exotic ideas floating around, like the possibility that dark matter itself could collapse into black holes under certain conditions, providing a population of seed black holes that we're not accounting for in our models. These ideas are highly speculative and face significant challenges, but they illustrate just how open this problem still is. Supermassive black holes aren't just passive occupants sitting at the centers of galaxies. They play an active and crucial role in shaping galactic evolution, regulating star formation, and determining the ultimate fate of their host galaxies. This might seem counterintuitive at first, because black holes are often portrayed as cosmic vacuum cleaners that suck up everything around them. But the reality is far more nuanced and interesting. The relationship between a galaxy and its central supermassive black hole is one of the most important and least intuitive discoveries in modern astronomy. As we mentioned earlier, there's a remarkably tight correlation between the mass of a galaxy's central black hole and the mass of its stellar bulge. This correlation, discovered in the early 2000s, was unexpected, because the event horizon of even the most massive, supermassive black hole is tiny compared to the size of a galaxy. Sagittarius A star, for instance, has an event horizon that would fit inside Mercury's orbit, but the Milky Way spans 100,000 light-years. The black hole occupies a region that's about 1/trillionth the diameter of the galaxy. How could something so small have such a profound influence on something so large? The answer lies in feedback. When a supermassive black hole actively feeds on surrounding matter, it doesn't just quietly consume that matter and grow larger. The accretion process is violent and energetic, releasing enormous amounts of radiation and often producing powerful jets that shoot material out at relativistic speeds. This energy output has consequences that extend far beyond the immediate vicinity of the black hole. The radiation from the accretion disk heats the surrounding gas, increasing its temperature and pressure. Hot gas has more thermal energy and is therefore more resistant to gravitational collapse. If you heat the gas in a galaxy's core enough, it becomes too hot to cool down and condense into dense clouds where stars can form. This is called radiative feedback, and it's one of the primary ways that supermassive black holes regulate star formation in their host galaxies. But radiative feedback is just one piece of the puzzle. The jets produced by actively feeding supermassive black holes can have even more dramatic effects. These jets plow through the surrounding gas like cosmic snowplows, pushing material out of the way and creating enormous bubbles or cavities in the gas. This mechanical feedback injects energy into the gas on scales of thousands or even millions of light-years, far beyond the immediate vicinity of the black hole itself. The gas that gets pushed around by these jets is heated, stirred up, and sometimes even expelled from the galaxy entirely. If you remove the gas from a galaxy or heat it to the point where it can't collapse and form stars, you effectively shut down star formation. Over time, the galaxy will exhaust its existing reservoir of gas as stars continue to form and die, but without new gas falling in to replenish it, star formation will gradually cease. This is exactly what we observe in many massive elliptical galaxies. These galaxies contain enormous amounts of gas, often visible as X-ray emitting halos surrounding the galaxy, but they're forming very few new stars. The gas is there, but it's too hot to collapse, kept at high temperatures by energy input from the central supermassive black hole. Without this feedback mechanism, the gas would cool down over time and fall toward the center of the galaxy, forming a massive burst of new stars. But the black hole prevents this from happening, maintaining a kind of equilibrium where the cooling of the gas is balanced by the heating from black hole activity. This feedback process helps explain why the most massive galaxies in the universe tend to be red and dead, composed primarily of old stars with very little ongoing star formation. It also explains the tight correlation between black hole mass and galaxy bulge mass. As a galaxy forms and grows, gas falls toward the center, feeding the central black hole and causing it to grow. But as the black hole grows, its feedback effects become stronger, heating more gas and shutting down star formation more efficiently. Eventually, the black hole grows large enough that its feedback effects are sufficient to regulate further growth, both of itself and of the galaxy. This creates a self-regulating system where the black hole and galaxy grow together until they reach a point of equilibrium. The ratio between black hole mass and bulge mass represents this equilibrium point, and it's remarkably consistent across a wide range of galaxy masses. This all sounds very neat and tidy, but like most things in astrophysics, the devil is in the details. We still don't fully understand all the mechanisms by which supermassive black holes influence their host galaxies, and there are ongoing debates about the relative importance of radiative versus mechanical feedback, how feedback operates in different types of galaxies, and whether our theoretical models accurately capture the complex physics involved. One thing we can say with confidence is that supermassive black holes are galactic architects, and without them, the universe would look very different. Galaxies would likely be smaller and more actively forming stars. The distribution of matter within galaxies would be different, and the overall evolution of cosmic structure would follow a different path. Now, what about our own galaxy and the supermassive black hole lurking at its center? Are we in danger? Should we be worried about Sagittarius A star suddenly waking up and devouring the solar system? The short answer is no, we're perfectly safe, but it's worth exploring why. First, let's talk about distance. The solar system is located about 27,000 light-years from the galactic center, in what's called the Orion arm of the Milky Way. We're orbiting the galactic center at a velocity of about 230 kilometers per second, and it takes us roughly 225 million years to complete one orbit. At this distance, the gravitational influence of Sagittarius A star on the solar system is negligible, compared to the combined gravitational pull of all the stars and dark matter between us and the galactic center. Even if Sagittarius A star were to suddenly become much more massive, say doubling or tripling in mass overnight, which is impossible, but let's imagine it anyway, the effect on the solar system's orbit would be minimal. We're simply too far away for the black hole's gravity to dominate our motion. But what if Sagittarius A star became active and started consuming large amounts of matter, brightening dramatically and producing powerful jets? Would that pose a danger? Again, the answer is no, primarily because of distance and geometry. If Sagittarius A star developed an accretion disk in jets, the jets would be oriented perpendicular to the plane of the accretion disk, and therefore roughly perpendicular to the galactic plane. The solar system, like most stars in the Milky Way, orbits within the galactic plane, so we wouldn't be in the line of fire of the jets. The radiation from a bright accretion disk would spread out in all directions, and by the time it reached us 27,000 light-years away, it would be diluted over an enormous area. Even a very luminous quasar, if placed at the galactic center, would appear bright in our sky. Perhaps as bright as the full moon, but it wouldn't be intense enough to cause any harm to life on Earth. Our atmosphere would shield us from any harmful high-energy radiation, and the total energy received would be far less than what we get from the sun every day. That said, if Sagittarius A star did become active, it would be an absolutely spectacular sight. The night sky would be dominated by a brilliant point of light at the galactic center, possibly surrounded by glowing clouds of gas illuminated by the black hole's radiation. Depending on how active it became and how much dust was in the way, it might be visible even during the daytime. Astronomers would have a field day studying it, and it would revolutionize our understanding of supermassive black holes. But it wouldn't pose any existential threat to humanity or life on Earth. Interestingly, there's strong evidence that Sagittarius A star was much more active in the relatively recent past. The Fermi bubbles, which we mentioned earlier, are enormous structures extending 25,000 light-years above and below the galactic plane, filled with high-energy gamma rays. These bubbles appear to be the remnant of a massive outburst from Sagittarius A star that occurred roughly 2 to 4 million years ago. During this outburst, the black hole was likely consuming matter at a much higher rate than it is today. producing a bright accretion disk and possibly jets that inflated these enormous bubbles. 2 to 4 million years ago, early human ancestors were walking around in Africa, and they would have seen a dramatically different night sky. The galactic center would have been much brighter, and depending on the intensity and duration of the outburst, it might have been one of the brightest objects in the sky. There's no evidence that this outburst had any negative effects on Earth or life at the time, which reinforces the point that we're at a safe distance from whatever the galactic center throws at us. But Sagittarius A star might not stay quiet forever. Simulations of the Milky Way's future suggest that in about 4 to 5 billion years, our galaxy will collide with the Andromeda galaxy. This won't be a violent collision in the sense of stars smashing into each other, because the distances between stars are so vast that stellar collisions will be extremely rare. But the gravitational interaction between the two galaxies will disrupt their structures, sending stars and gas clouds onto new orbits. Some of this gas will inevitably end up falling toward the merged galactic center, where Sagittarius A star and Andromeda's central black hole, which is about twice as massive, will eventually merge. This process of galaxy merger and black hole merger will likely trigger a period of intense activity, with both black holes feeding heavily before they finally coalesce. The result will be a single supermassive black hole with a mass of roughly 230 million solar masses, surrounded by a bright accretion disk and possibly producing jets. This will occur over a timescale of millions of years, and by that point, if humanity or any of our descendants are still around, they'll have a front row seat to one of the most spectacular cosmic events imaginable. There's even a small but non-zero chance that during the galaxy merger, the solar system could be ejected from the galaxy entirely, flung out into intergalactic space by a gravitational interaction with passing stars. But again, this is nothing to worry about on human timescales. These events are billions of years in the future, and the Sun will have already expanded into a red giant and swallowed the inner planets long before the Milky Way and Andromeda collide. Speaking of the far future, let's talk about what happens to supermassive black holes over truly cosmic timescales. Right now, the universe is about 13.8 billion years old, which feels ancient. But in terms of the universe's total lifespan, we're still in the very early chapters of the story. Stars will continue forming for trillions of years, gradually exhausting the supply of hydrogen gas. Eventually, star formation will cease, and the universe will enter what cosmologists call the degenerate era, dominated by slowly cooling stellar remnants like white dwarfs, neutron stars, and black holes. On timescales of 10 to the power of 20 years or so, galaxies will gradually evaporate as stars are ejected through gravitational interactions. Close encounters between stars will occasionally send one star flying out of the galaxy at high velocity, and over immense spans of time, galaxies will slowly lose stars this way. The remaining stars will gradually spiral inward due to the emission of gravitational waves, an extremely weak effect that only becomes noticeable over absurdly long timescales, eventually falling into the central supermassive black hole. After the degenerate era comes the black hole era, when the universe is dominated by black holes of various sizes, from stellar remnants to the supermassive giants at the cores of long-dead galaxies. These black holes will be essentially the only significant structures left, floating in a cold, dark, ever-expanding universe. But even black holes aren't eternal. Stephen Hawking demonstrated in the 1970s that black holes emit radiation due to quantum mechanical effects near the event horizon. This Hawking radiation causes black holes to very slowly lose mass over time, eventually evaporating completely. The time scale for this process is stupendously long, scaling with the cube of the black hole's mass. A stellar mass black hole of 10 solar masses would take about 10 to the power of 67 years to evaporate. That's a 1 followed by 67 zeros, a number so large it's essentially meaningless. For comparison, the current age of the universe is only about 10 to the power of 10 years. For a supermassive black hole like a Sagittarius A star at 4 million solar masses, the evaporation time would be approximately 10 to the power of 87 years. For Taun 618 at 66 billion solar masses, you're looking at around 10 to the power of 100 years. These timescales are so far beyond anything we can meaningfully comprehend that they might as well be infinite for all practical purposes. But in principle, given enough time, even the most massive black holes will eventually radiate away all their mass and disappear in a final burst of Hawking radiation. After the black hole era, sometime around 10 to the power of 100 years or later, the universe will enter what's called the dark era, a time when all the black holes have evaporated, all the stars have long since burned out, and the universe consists of nothing but extremely dilute radiation. Fundamental particles scattered across vast distances, and the ever-accelerating expansion of space driven by dark energy. At this point, the universe will be cold, dark, and essentially empty, with any two particles separated by distances vastly larger than the observable universe is today. But we're getting pretty far afield here. Let's bring it back to something a bit more tangible. If you could somehow visit one of these supermassive black holes, what would you actually see and experience? Let's take Taun 618 as our example because it's so massive that some of the more extreme effects of black holes are actually less extreme near its event horizon. Imagine you're in a spacecraft approaching Taun 618 from a great distance. At first, you wouldn't see the black hole itself because, by definition, it doesn't emit light. But you'd see the accretion disk, an enormous glowing structure of superheated material orbiting the black hole. This disk would be blindingly bright, potentially brighter than anything else in your field of view, pumping out more energy than hundreds of trillions of stars. The light from the accretion disk would be shifted in frequency depending on the motion of the emitting material. Material moving toward you would be blue shifted, appearing bluer and brighter, while material moving away would be red shifted, appearing redder and dimmer. As you got closer, you'd start to see the gravitational lensing effects of the black hole. Light from background objects, stars, or galaxies behind the black hole would have its path bent by the curvature of spacetime, creating distorted, stretched, or multiple images. If you were at the right angle, you might see an Einstein ring, a complete circle of light formed by the bending of light from a background object directly behind the black hole. As you continued your approach, you'd eventually see the shadow of the black hole, a dark circle against the glowing background of the accretion disk. This shadow would be larger than the event horizon itself, about 2.5 times the Schwarzschild radius, because light rays that pass close to the black hole get captured or deflected away, even if they're outside the event horizon. For Taun 618, this shadow would appear enormous, spanning several days' worth of light travel time across. Now, let's say you've decided to cross the event horizon, perhaps for science, or perhaps because you've made some questionable life choices. As you approach, you would notice time dilation effects becoming significant. If you're watching a clock on a distant spacecraft that's remaining far from the black hole, you'd see it ticking faster and faster from your perspective as you fall deeper into the gravitational well. Meanwhile, observers on that distant spacecraft watching you would see your clock ticking slower and slower, and they'd see you appear to slow down as you approach the event horizon, asymptotically approaching but never quite reaching it from their perspective. But from your perspective, nothing special happens at the event horizon. You'd cross it in a finite amount of your own time, and there wouldn't be any dramatic sign or marker indicating that you'd passed the point of no return. Because TON 618 is so massive, the tidal forces at the event horizon are actually quite gentle. The difference in gravitational pull between your head and your feet, if you're falling feet first, would be noticeable but not lethal. You could potentially survive crossing the event horizon and continue falling inward for some time before the tidal forces became strong enough to tear you apart. As you fall inward past the event horizon, the geometry of spacetime has changed in a fundamental way. All paths now lead inward toward the singularity. There's no trajectory, no amount of thrust, no clever maneuvering that could bring you back out. Attempting to escape would be like trying to travel backward in time. It's not that you lack the technology or the fuel, it's that the direction you want to go no longer exists as a possibility. The singularity is not a place in space that you're falling toward. It's a moment in your future, inevitable and approaching, roughly analogous to how your next birthday is inevitable and approaching. As you continue falling, getting closer to the singularity at the center, the tidal forces would ramp up exponentially. Eventually, you would reach a point where the difference in gravitational pull across your body would exceed the molecular forces holding you together, and you'd be stretched into a long, thin stream of atoms. This spaghettification process would accelerate, with the tidal forces continuing to increase as you approach the singularity. At some point, even the atoms themselves would be torn apart. Then the atomic nuclei, then perhaps even the fundamental particles, until finally you'd reach the singularity, a point of infinite density and infinite curvature, where the laws of physics as we understand them completely break down. What happens at the singularity is genuinely unknown. General relativity predicts that the curvature of spacetime becomes infinite, which is a mathematical way of saying that the theory has stopped working. At this point, quantum mechanical effects, which general relativity doesn't account for, should become important, but we don't have a complete theory of quantum gravity to tell us what actually happens. This is one of the great unsolved problems in theoretical physics. Some physicists speculate that there might not be a true singularity, that quantum effects might prevent the density from becoming infinite, creating instead some kind of highly compressed but finite state. Others suggest that the singularity might be a doorway to another region of spacetime, perhaps even another universe, though there's no observational evidence for this and it remains pure speculation. For now, the singularity remains a place where our physics breaks down, a boundary beyond which we cannot see, either literally or figuratively. Now, let's compare this experience to visiting a smaller black hole, say a stellar mass black hole of 10 solar masses. The event horizon of this black hole would have a radius of only about 30 kilometers, compared to 195 billion kilometers for TON 618. The tidal forces at the event horizon of the stellar mass black hole would be about 12 billion times stronger than those at the event horizon of TON 618, because tidal forces scale inversely with the square of the distance to the center, and the event horizon is much closer to the center for smaller black holes. You'd be ripped apart by tidal forces long before you reached the event horizon of a stellar mass black hole, stretched into a long strand of atoms while still thousands of kilometers away. There would be no chance to calmly observe the crossing of the event horizon. Your death would be violent and would occur well outside the point of no return. This is why science fiction often features enormous black holes like Gargantua from the movie Interstellar. If you want your characters to survive close approaches to a black hole and potentially even cross the event horizon while remaining intact, you need a supermassive black hole. Interestingly, the black hole Gargantua in Interstellar was based on real physics, calculated by physicist Kip Thorne to have a mass of about 100 million solar masses. This was chosen specifically so that the tidal forces near the event horizon would be survivable, and so that time dilation effects would be strong enough to explain the plot point where time passes much more slowly on a planet near the black hole than it does farther away. However, 100 million solar masses is actually on the smaller end of supermassive black holes. Gargantua would be smaller than the black hole in Andromeda and only about 25 times more massive than Sagittarius A star. Compared to true monsters like Taun 618 or Phoenix A, Gargantua is a lightweight. If the movie had used one of the ultramassive black holes we've discussed, the time dilation effects could have been even more extreme. But this raises an interesting point about what supermassive black holes teach us about the universe. These objects exist at the boundary of our understanding, where the predictions of general relativity become most extreme and where our intuitions about space and time completely fail. They're natural laboratories for testing our theories of gravity in regimes that we could never reproduce on Earth. By observing supermassive black holes, studying their effects on surrounding matter, and eventually detecting gravitational waves from their mergers, we learn about the fundamental nature of space-time itself. They also represent a kind of cosmic endpoint. Matter that falls into a black hole is removed from the universe in a very real sense. The information about what that matter was made of, its history, its structure, all of that is lost, hidden behind the event horizon. Or is it? The black hole information paradox, first articulated by Stephen Hawking, points out a conflict between general relativity and quantum mechanics. According to quantum mechanics, information cannot be destroyed, but according to general relativity, anything that falls into a black hole is gone forever. And when the black hole eventually evaporates through Hawking radiation, that information is lost. This paradox has been one of the driving forces behind attempts to develop a theory of quantum gravity that would unify general relativity and quantum mechanics. Recent work suggests that information might actually be preserved in subtle correlations in the Hawking radiation. But the details are still being worked out, and it remains an active area of research. Supermassive black holes also connect to some of the deepest questions in cosmology. Why does the universe have the large-scale structure we observe? Why are galaxies the sizes they are? Why is star formation distributed the way it is across cosmic history? All of these questions involve supermassive black holes and their feedback effects. In a very real sense, supermassive black holes are responsible for the universe looking the way it does. Without them, galaxies would be different, the distribution of matter would be different, and the history of star formation would follow a different trajectory. And that means the formation of planets, the emergence of life, and ultimately the existence of beings capable of looking up at the sky and wondering about black holes. All of this is connected to the presence of supermassive black holes.